Okay, so now in this video, I'm going to talk about units, subgroups, finite subgroups of units. Okay, so one of the main goals. So there's a lot of consequences of this theorem. This is kind of a beautiful theorem that we're going to prove. The goals kind of are. So I mean, like, what are the outcomes or the goals? Is that we'll be able to talk about. So we can talk about. So talk about roots of unity in general fields. So not just C. Okay, and so some consequences of what we're going to do is we're going to show that all groups of roots of unity let's say so say all shows that, so that show the group of roots of unity in any field is cyclic. Okay, I need, and then let me just finish these other things. So, okay, so another big consequence is that all finite fields of the same cardinality will be isomorphic. That's huge. That's something that we talked about before when we were computing finite fields. And I didn't really show you how to do this. And then I guess, like I said, like that goes in this first part. Like we'll be able to talk about cyclotomic fields in more general fields. I'm getting a little lag here, so I'm going to stop the video for a second and then continue. Okay. All right. So this is the goal of what I want to do in this video, and now I'm going to prove the theorem. Okay. So state and prove the theorem. So let's just talk about subgroups of units. So what? Okay, there we go. So here's the theorem. Ooh. Theorem. Right? So let K be a field. Right? Any finite subgroup of K cross is cyclic. That's it. That's all I'm going to prove. All right, so let's prove this. Proof. Okay, so the proof is really cool. So the proof uses the fundamental theorem of abelian groups, right? In this invariant factors, elementary divisors thing. So all right, and so let M be a subset. So what I'm going to do is I'm going to use that this is a finitely generated, or in particularly a finite abelian group, be a finite group, and I'm going to show that this is cyclic. Okay, so it's abelian, right? Since it's abelian, we get to use that theorem. Is abelian, right? M, and it's finite. It's isomorphic to Z mod A1 of Z, direct sum Z mod A2 of Z, direct sum Z mod AR of Z, where the AI are the elementary divisors and just as kind of like a general warning for the uninitiated that depending on what book you read, people will say elementary divisor or invariant factor, and they just kind of like, people are all over the place on the terminology. So, but what I mean is, these are the elementary divisors satisfying, and this is here A1 divides A2 divides A3 divides all the way up to AR. So this is the biggest one, and the AR is the biggest one, and it has all the prime factors. Okay? Okay. So now using this isomorphism, right, we can look at generators of these things. So, okay, so corresponding, so here's what we'll do. So corresponding to the generator, of, or a generator of Z mod A1Z, there is an element, is some zeta in M such that zeta to the A1 is equal to 1, right? And so by the fundamental theorem of algebra, so, by fundamental theorem, let's say by factorization, of x to the A1 minus 1, there can be at most A1 such zeta in K, satisfying this particular equation. That's an equal sign right there. No, that's not an equal sign. Factorization of this, okay? So there could be at most A1 of these things, okay? All right. So similarly, here's the issue, is that we're going to get a contradiction, right? So, I mean, we're not quite going to get a contradiction. We're going to end up showing that this, and let me show you what I mean by this. This is it. All this crap will go away, and that this is the only thing that we can have. Okay, but let me prove that. So the issue is that since A1 divides A2, if A2 was existed, right? So we can write A2 is equal to A1 A2 tilde, and corresponding to a generator of this, to the generator of Z mod A2 of Z, right? There is some zeta 2 in M such that, well, now I do zeta 2 to the A2 is equal to 1, right? But here's the deal. Zeta 2 to the A2, zeta 2 to the A2, this is zeta 2, well, now let's use this, to the A1 A2 tilde, and this is zeta 2 to the A2 tilde to the A1. And this gives a new element, right? So this now gives a new element. So this gives a new element satisfying this equation, x to the A1 minus 1 is equal to 0. That's a contradiction. We could only have n of them, and we had n of them. Or we can only have A1 of them, and we had A1 of them, right? So only have A1 of them, and we found them all. All right, so this implies that A1 is equal to AR. Right? A1 is equal to, A1 is well, AR is equal to A1, right? And these are all of the, there's only and let's say and R is equal to 1, right? Okay, so very cool. All right, so now any subgroup, any finite subgroup of K cross is, okay, so we proved this. Any finite subgroup of K cross is cyclic. Okay, so as a consequence, we have a very non-trivial corollary. Here's our first non-trivial corollary. Right. So let Q be P to the R, where P is prime, is a rational prime, and R is an integer. Right? So the group FQ cross is cyclic. That is cool. And it's cyclic of order P to the R minus 1. All right? So now we proved that the group of units in any finite field is a cyclic group, which is not obvious. So in particular, so if we took like F4, so this was isomorphic to F2 of x mod x squared plus x plus 1, right? Well, okay, I guess this one we didn't know because 4 minus 3 is 2. But this is, okay, that's kind of silly because there's only one group of order 3, right? But anyway, F4 cross is isomorphic to C3. But I mean, okay, let's, F8. So this is isomorphic to, oh, that's 7 as well. 7. Dang it. Let's see. Okay, so this one's isomorphic to F7. Okay, so I think F16. Okay, that's 15. Okay, so this thing here. So this thing has 15 elements. So this is the first one that's non-trivial. Oh, sorry, not F7, C7. C7. But this field F8 is isomorphic to F4 join X modulo X squared plus X plus U, I think. So for U in F4. And I think that we can do this. So this is F16. So this thing is isomorphic to C15. And now we didn't really know it was C15. It could have been C5 cross C3, right? But that doesn't happen. That's the point. I guess we could have, another way to do it is we could have shown that C7 is inside C15. Let's see, C7 is F8 cross. Yeah, that's right, huh? What am I doing wrong here? Because 7 does not divide 15. Anyway, this does work. This has some weird description. This is F8 adjoin X, and I think you can do X squared plus X plus V, where V is some element of F16, or F8. F8. And my thing here is that okay, so F, and this is 7 elements. 7 does not divide 15, so what the heck is going on? One second, let me think about this. Okay, so here's what was going wrong here. This is not contained in here, right? This, okay, so this is not right. Right, and this is not right. Right, so let's count the elements of this field. This is something here, right? But let's just count elements of the elements in this ring, and they have the form A plus BX like this, and so BX bar. So this is an element of this field, and how many options are there for this? Well, there's 4 because of this coefficient field, and there's 4 here. And this is 4 times 4, which is 16. and this is F16, not F8. Okay, so that was the issue here, and that explains this. So here we in particular we don't have this either, right? So this thing is F16, but we do have that's the bad thing. The thing that we can see is that this one is a sub thing of this. So here we do have that C3 is a subgroup of C15. Okay, so that's what clears this up. So yeah, okay. So all right, that's one of the applications, is that we can compute these, okay, and so the other corollary is that if K is any field, and we define so mu n K, so this thing is equal to the set of A in K cross such that A to the n is equal to 1, right, is a cyclic group. And so this is the group, this is the set of nth root of unity. So this is the nth roots of unity in K, right? So K doesn't need to be algebraically closed. It doesn't need to be the complex numbers. It is just any field. And for any field like this, we have the cyclic group we have this, that this group is cyclic. Okay, so that's cool. And what's going to happen is we're going to use this. So one of the next things to do is we're going to use this to prove that all finite fields of the same cardinality are isomorphic. Okay, so this allows us, so will allow us all finite fields of the same cardinality are isomorphic. All right, so let me do that.